Okay, so in this lecture, we're going to study how to evaluate limits and actually compute these numerical values. In the previous lecture, we talked about the notion of a limit and what it means for a function to approach a value as the input approaches some given value. Now, this is going to be a pretty straightforward lecture. It might be long, but you're going to learn the basic rules behind evaluating limits. And with respect to the homework and with respect to exams, this is kind of important, right? You need to be able to compute something. However, I feel like I would be doing a disservice to you if I didn't, along the way, as we're computing these numerical values, discuss the theory and remind you that calculus is all about ideas, right? All of mathematics is really about ideas, and it kind of gets forgotten about when you're dealing with the headache of trying to find this answer. Now, it's been my experience dealing with students that this is actually a problem. And this is why some students struggle in a course like calculus or even like pre-cal or college algebra. Students are so concerned about the answer that they start doing, like trying to write something, they start acting before they think. And this was actually my problem when I was a student. When I was trying to learn math, I thought that I just needed to start working on the thing and trying to get the answer so I could put it on an exam or answer on an exam. But that's really not the way that you should think about mathematics, and I hope that you don't think about that in my course throughout the semester. What I would like you to do before you try solving some given problem, for example, pause and think about what's happening before you put your pen to paper. Just think for a moment, take a step back and breathe. Okay, what am I actually looking at? And then from there, then you can start using the tools of algebra and writing to figure out a way to respond to the problem. So very important point in this class and in all your other math classes, pause, then do, okay? So on that note, even though we're gonna be solving all kinds of problems today, I'd like to remind you about the limiting process. Okay. So the formal definition is something like, and this is kind of an abbreviated version of it. So we write the limit of f of x equals some number L as x approaches c whenever for any choice of epsilon greater than 0. Remember that epsilon in mathematics typically means a small positive number. So for any choice of epsilon greater than 0, there is some delta greater than 0 such that if x is within distance delta to that number c, then the distance from the function to the number L, which is called the limit, is less than epsilon. Okay, that's just recalling the very last thing that we covered in the previous lecture. But again, it's a bunch of jumble to you, most likely, right? The absolute values, the deltas, the epsilon, all this formal stuff, whatever. It's messy. But what's the idea, right? The idea is that this is true whenever, and I'm going to write this in like layman's terms. So the limit of this function equals a number L as x approaches c whenever there is an interval, open interval, around C so that the distance maybe instead of saying there is an interval, there is some interval around C so that the distance from f of x to L is small as we would like for x in this interval. Running out of room, that's this interval. So this definition is saying that the limit of f of x as x approaches C is equal to a number L. That is true whenever there's always some interval around C that makes the function as close as we want to the limit. That's what it's saying. Probably should have wrote that, but too late now. But that's the idea, right? So with this idea, there are a few immediate observations that we can observe about very simple functions, right? I mentioned last time that we were dealing with these weird, complicated functions. Now we're going to look at the simple functions and kind of build up from them. So what are the simple functions? Well, before I write them down, I'm going to say that this is actually a theorem. And theorems are mathematical statements that need to be proven. Now, I'm not going to prove these theorems that we covered today in class. However, I am tempted, if I have time, to make extra videos for you guys showing how to prove in a formal sense the following statements. And these statements are, part one, the limit as x approaches C of B is equal to B. Now this is if your function f in question is equal to B, is a constant function. Right, so B is just some real number. Okay, so that's part one of this theorem. But before I move to the other parts, why would this make sense? What does a constant function even look like, right? Well, suppose, for example, f of x is equal to like 2. That's a constant function. No matter what value of x you plug into this function, it just returns the number 2. What does the graph look like? The graph, plot of f of x, looks like this. Okay. It's just a horizontal line that intersects the y-axis at y is equal to 2. Okay. No matter what we input to this function, it always returns 2. It's that horizontal line. Now, why would this make sense that the limit as x approaches any number c of this function will be 2? Because that's what this is saying, right? I don't know. If this is c, I guess I'll pick a value like 1 or something, right? As I approach c on the x values or the x-axis, what is the value of f? Well, 2, 2, 2, 2, 2. It's going towards 2, okay? If I come from the right-hand side, 2, 2, 2, 2. It's also approaching 2 as x approaches c, right? And that's the whole idea, that we can make this function here arbitrarily close to 2. That's the limit, right? It's actually equal to everywhere, but it's always close to it. We can always find an interval around c where this function is arbitrarily close to 2. It happens to equal it, but that's the idea. So hopefully this statement here makes sense. If you have a constant function and you try to evaluate the limit as x approaches any number c, it's always just the value of the constant. Hopefully that makes sense. Okay, that's part 1. Part 2. Limit as x approaches c of x is just equal to c. So again, before we use it, we need to probably reason about it a little bit, right? So hopefully all of you know what that function looks like. This function, f of x equals to x, that is a line, right? It's a line passing through the origin, right? So if I look at the plot of the graph of f of x, it looks like this. That is a pretty straight line. I'm pretty psyched on that. So, okay, there's my f of x function, right? Now, again, if we want to know the behavior of that function as x approaches some value, it's really simple, right? Take, for example, 2. Right, so what if c is equal to 2? Well, as we start heading that way, right? I'll maybe use like green or something. When c is equal to 1, the function's value is there at 1. When c is equal to 1.5, we're right there. When c is equal to 1.7, we're like right there. 1.9, right there. Where are we going? We're heading towards 2. And so that was going this way. What if we come at c from that way? Sorry, I just thought about that meme that's like, come at me, bro. It's the same type of pattern. But so what if we're coming at c from the right-hand side, right? Well, when c is 3, we're up here. When c is not c, when x is 3, the function's value is 3. When x is 2.5, the function's value is 2.5. And as we go down, this is where we're going, right? So hopefully this makes sense. We can make this function, f of x equal to x, as close as we want to 2, just depending on the interval around c that we want to choose, right? Like if we wanted, this is actually probably a good example to illustrate this definition again. Don't want to get rid of my nice line there. Okay, so 1, 2. Right, like we can pick any, so this is the proposed limit right there, right? No matter how small of an interval that we want to pick around that thing, if we can make it as small as we want, then it's really easy to pick an interval around c to push everything from the function into that range. Let's pick the same size. And then you pick any x in there, it's going to be inside that interval. And it doesn't matter how big that interval is. We can make it as small as we want. We can always find an interval around C so that that function's value is squeezed as close as we want to C. So, and this is for any value C. I picked 2 in this case, but we can really use whatever value we want.
The concept makes sense to me, but which interval is which?
So this right here, thank you for that question. This is the epsilon interval. Right there. That's this. Right? The function is within epsilon to the limit. In this case, the limit is 2. Okay? So we need to be able to find an interval around C, which in this case, it happens to be the same size interval. So this right here would be the delta interval. Okay? And if we look back to the definition, this is a conditional statement. If that, then that better happen. Right? So if we pick anything in there, notice where it gets sent. It's inside there. If x is in that interval, then f evaluated at that x is in that interval. Okay?
Got it. Thank you.
So in the thing that's important is that this interval can be as small as we want, no matter how big it is, it doesn't matter. But as long as we can find something around that one, so that if we pick any x in there, f of x gets put in there, we're good. Okay. Thank you for the question. I like it when the students interact because I don't feel like I'm talking at a void. So, thank you. Okay, so limit of x for any c is going to be c. And just going to the same value. Okay. Next up, part 3. So the limit of x to the power n is equal to c to the power n, again, as x approaches c. And this is for any natural number n. It's like a whole, actually, I should say, yeah, so it's a whole positive number, right? Now, it's important to think about why this might work. So earlier, I've drawn a few graphs illustrating the limiting process, right? We have some curve in the Euclidean plane, and the curve y values approach a given value as x approaches c from both sides, right? So that hopefully makes sense for this one. Hopefully it also makes sense for this one, right? And the choice of n, maybe we can adapt in a little bit, but currently it's just any counting number, like 1, 2, 3, 4, so forth and so on, right? So for example, if I look at something like this, this looks maybe like, it looks like the graph of f of x equals to x to the power 4. It's like a fat parabola, right? Now, this is a smooth looking thing, right? It's smooth. There's no discontinuities anywhere. There's no worry about dividing by 0. Right? So if we approach any value c from the left-hand side or from the right-hand side, the function is not going to have a problem approaching some number. In this case, that number, right? It's not going to have any problems. We only really have to worry about the limiting process when there's possible jump discontinuities, when from the left-hand side and the right-hand side, the function approaches two different values. That's a bad thing, right? Then the limit wouldn't exist. Or if we're approaching a value and the function blows up to infinity, that's another problem, right? Or if the function like oscillates forever as x approaches some value c. That thing right there is smooth. There's no problems to worry about. What is the function approaching if x approaches c from both sides? It's just basically evaluating the function at that number. There's no discontinuities. It's not jumping around. It's good to go. So in that case, we can literally just take O. In this case, it'll be c to the power 4. So that would be the limit here. And that's what this part 3 of the theorem states. Does that make sense, maybe? Again, it's a nice, smooth, fat parabola. It's good. Okay? There's no holes.
Seeds.
Yeah, it's good. So, all right. There might be a problem though if we don't have a natural number. Like, what if we had like a negative positive whole number, right? Like, what if that power was negative, right? So what about, or what about if it was a ratio, like 1/2? X to the power of 1/2 is the same thing as saying the square root, right? Square root of x. So then we might have a problem just by looking at the graph. The graph of this, so this would be f of x equals to x to the power 1/2, right? That function is not even defined over here anywhere, right? Then we might have some problems. So we'll come back to that in another theorem. But for now, I think we're safe with this theorem here. Limit of a constant is just the constant. Limit of x as x approaches c is just c. And then the limit of x to the power n, where n is a natural number, 1, 2, 3, whatever, is just c to the power n. So I think we're safe right now because those are nice looking things. Now, when we have to deal with domain issues where the power might not be a whole number, or it might be negative or we're like dividing, gotta be careful. So, but again, we'll encounter these as we move on. Okay. Okay. Next up, a rather big theorem. And I always hate teaching or like lecturing this theorem because it's so, there's so many parts to it. So I'm just going to write it down and talk you through it. I won't look at the camera. I'm just going to get it out the way and then we'll discuss it. So this is indeed a theorem, which again means it's a true statement that has been proven at some point. Okay. So suppose B is some real number. So whenever I write the epsilon symbol there, it means it's just contained in there. So it's a real number. And, well, maybe not and, I'll use a comma. The limit as x approaches c of f of x is equal to L, comma, and the limit as x approaches c of g of x equals some number k. So I'm not writing up a full statement, and I need to like remind you, or not remind you, but tell you that when I write limit of a function equals some number here, some letter here, I'm implying that the limit not only exists, but it's some real number, and that's what that means. It exists, it's a real number. That's what that implies. So limit of f of x exists as x approaches c, it's equal to L, and limit of x as x approaches c of g of x equals k. So I'm supposing that those limits exist, and they're denoted by L and k respectively. Okay. Now, this theorem, as I was just mentioning, has a few parts. the limit as x approaches c of b times f of x is equal to b times L. Okay. So what this is saying is that for any scalar multiple b, we can essentially take it out of the limit and evaluate the limit of f of x on its own and then multiply back by that scalar multiple. So whenever you see that b is a real number or any letter is a real number, it's multiplying something, it's typically called a scalar. It's scaling the value. So what's happening here is you're scaling the function f, which we're assuming converges to some number L. And if we do that, then taking the limit of that scaled version is just the scaling of the limit. That's what that's saying. Next up, we have the limit as x approaches c of f of x either plus or minus g of x is equal to the limit of the first function plus or minus, respectively, the limit of the second function. Okay. So we'd say that the limit is additive in this sense. We can sort of distribute the limit over sums and differences of functions, provided those limits exist, which we assumed in the supposition of the theorem that they do. Okay. And in a likewise manner, multiplication also works out. So the limit as x approaches c of f of x times g of x is equal to L times k, provided f converges to L and g converges to k. Okay, and this also implies that the limit as x approaches c of the difference of these convergent functions is equal to the difference, or not the difference, the ratio. The ratio of these convergent functions, taking the limit, is equal to the ratio of the limits. Now, you have to be careful. Why do you have to be careful? We have not specified any conditions currently on k, right? So what if g converges to 0 as x approaches c? Then we have division by 0. That's not going to work out. Okay, so there's an extra condition here saying provided k is not equal to 0. It's really important to note that you can only evaluate the limit of a ratio as the ratio of limits when the denominator limiting value is non-zero. Okay.
So for this number 4, then the limit would not exist if k is 0.
Exactly. Good call. I probably should have said that myself. But yes, if the denominator limiting value is 0, it's not going to exist. Okay. And then there's one more part to this theorem, part 5. And that says that the limit as x approaches c of f of x to the power n is equal to L to the power n. Now again, we have to be careful about the properties of n here, right? For example, what if n was 1/2 and the limit of f was -1? Then we would be taking the square root of a negative number. We're not dealing with complex imaginary numbers right now. It's not going to exist, right? Or if n was something like, if the power here was -1, right? Then if L was 0, we'd have some weird possible division by 0, right? So we're going to specify for now that this is true when n is a natural number. And natural numbers are the counting numbers. They're the numbers starting at 1 and then incrementing in unit intervals after that. It turns out we'll be okay with other conditions on n, but for now, when we start, we'll have that n as just a natural number, and then we'll discover the other possibilities with the following theorems. Okay. So I feel like this is a good place to pause the video. Okay, and we're back. So we have two theorems that provide different ways, different rules, which I hate that word, but different rules for evaluating limits. So here I've written on the board an example problem. Now, before writing anything down, as I was mentioning earlier, first, pause and think about what's going on with the problem. Before trying to apply the rules, pause and think. This function here, 4x squared plus 3. What type of function is this? It's a polynomial function, right? Do we really have to worry about anything? Right, yeah, like this is, we're never gonna have to worry about this function heading towards some division error, some square root of negative thing. It's not blowing up as we approach the number. It's well behaved. It's smooth. It's continuous. If you remember talking about continuity in like a pre-calc course, right? So I bet that this thing, before doing anything, just looking at it, I bet you if I just plug in that number 2, that's going to be the limit. Because what else could possibly happen, right? Like, I don't see a problem happening. So what would that be? So 2 squared is 4, 4 times 4, 16, 19. So my guess before applying any of these rules is 19. Now, this is something I want to try my best to instill in all of you, that before you do anything, as you're thinking about the problem, you get a sense of what the answer should be. Having a sense of what it should be will tell you whether or not you're in the ballpark when you start trying to apply these rules that you're memorizing for whatever reason. So my guess is this is going to be, or should be, close to 19. I'm almost positive it'll be exactly. Well, I am positive, but if I were pretending like I didn't know anything, I would say it should be around 19. Okay. So now let's use these rules that we've learned. I erased a few, but hopefully you remember them. And write out every step to figuring out what this limit is. Okay. One more thing. Pay attention to how I write my solutions. I plan on giving all of you take-home exams, not multiple choice problems, but take-home written exams. When you write your solutions, mimic exactly what I do. I want to see the start of the solution, and then I want to see your answer, and then I'll tell you how to end your answer in a moment. Okay. little side note. This problem. So I'm concerned, for whatever reason, about the behavior of this polynomial as the input approaches 2 from the left and right hand sides. It's smooth, I'm not expecting any problems, so I should be able to just work through it. Now, currently I see a limit of a sum where over here in this previous theorem, I observe that the limit of the sum of functions is the sum of the limits, if the limits exist. So what I'm going to do is split this sum of variables and scalars and all that business. I'm going to split it up into several different limits and see what happens. So the limit of the sum is the sum of the limits. That's the best way to think about it. So limit as x approaches 2 of 4x squared, that's the first term, plus limit as x approaches 2 of the constant function 3. Now, the first theorem that I wrote down today dealt with these constant things, right? The limit, no matter what x is approaching of a constant, is just the constant value. So that limit should be
3.
3. Okay. So we know that I'm going to have a 3 over here. Now, looking at this guy right here, the first piece, I see that I have a scalar multiple of that function. If I come back to this previous theorem, I see that you can essentially take the scalars outside of the limit and then evaluate the limit of the function on the inside. So I'm going to go ahead and take that scalar and move it out. And I'm also going to notice that once I do take that scalar out, because I'm running in a boardroom, honestly, but I'll notice that if I take the scalar out, I'm left with x squared on the inside. Another way of writing x squared is to say in brackets x, close brackets, all squared. Like that. Now, this power, right, that's a natural number. It's one of the counting numbers. So the limit of that term is the limit of the inside to the power 2. And the first theorem that I wrote down tells me what this is. In fact, I'll just kind of isolate it. What is that limit right there? Inside of that little rectangle, what's that limit?
2 squared.
So here it'll be 2, right? I think you were jumping ahead and squaring it, but like inside that box, it's 2.
Oh yeah, correct.
There you go, right? So that's not so bad. Like in there, it's 2. So I think that this abstract idea of breaking the problem into these little constituent pieces is something that at your current like knowledge level of mathematics still might be new. It's really helpful for those of you that might be struggling to really break down every single little thing in what you're looking at into the smallest pieces possible and not jumping ahead, right? Like if I had more boardroom, honestly, I would have written x squared inside of there and then had another line pulling the power out, because I find that that helps students that are struggling. So if you are struggling in math, it helps to have every single step, slight changes just listed so that if you do make a problem, you can catch it. I'm like ranting, but back to the problem. Inside that little box right there, that will be 2 by theorem, the first theorem, second part that I wrote. So I will have 4 times the outside times the inside squared plus that value 3 there. And what does this evaluate to? $19. Go ahead and box it in. So in your solution, if you're submitting to me this problem, there wouldn't be a little blue box right here, but there would be a box around your final answer. Okay. Now, it's important to remember that before we even got to this answer, we knew before we wrote anything down that the solution should be something close to that number. And then we applied algebra and these limiting properties through the theorems, and we get to a number that's 19. At that point, you should feel moderately confident that you have the correct answer. If your initial guess plus the answer you arrive at are in the same range, you're probably on the right track. And they match up exactly, I'm happy, done. And you should as well when you're working through these problems. Okay. Now, I was somewhat hinting at the following theorem when I said that that's a polynomial. It's smooth, there's no holes. We should kind of expect it to behave a certain way as x approaches some value. Right? We should just actually be able to plug it in. And that is the next theorem, actually. So again, polynomials are just coefficients and powers of x in a sum. Look like that. And these, we can evaluate the limit really easily. And that's the following theorem. And it states that if P is a polynomial function, and C is any real number, there's that epsilon business again, C is a real number, then the limit as x approaches C of P of x is precisely P of C. That should make sense if you just imagine every single polynomial that you've ever been exposed to. And these are these curvy looking things, the linear function, the cubic function, parabolas. Where would there ever be a problem with the behavior of the function? And I keep on saying this word behavior because I'm trying to emphasize it. When we're looking at functions in this course, and in general, to be better at math courses, you have to try to like imagine what's happening. Polynomials have no holes and are smooth looking. We should not expect this thing to do, this function to do anything drastic as we're heading towards some value C. It's just going to behave normal. There's nothing to worry about. So that's like an informal but intuitive way of thinking about why this is true, which we already kind of thought about with this problem before we worked it out with the rules, which I hate saying that word because personally I have a pretty bad memory. And one of my problems in mathematics is I was trying my best to learn it at the beginning, was I was just memorizing everything and I wasn't thinking. Thinking about the object is easier to me than memorizing the rules. So on that note, we can probably think about this theorem on polynomials, which, by the way, if you didn't already catch on, means that that's a polynomial. We could have just plugged in 2 for x and been done with it using that theorem instead of working through these rules. But what else can we maybe deduce from this theorem? What's a corollary? A corollary is a result that follows from a theorem. So what's something that this would imply? What are some other functions that maybe make use of polynomials? Well,
I understand this theorem that you're talking about. I just have a question. What is that little E symbol? What does that mean?
Yeah, that's the epsilon.
Yeah, epsilon. Okay.
Yeah, so thank you for bringing that up. So where do I have room to write this?
Sorry, I mostly get what you're teaching, but these symbols kind of weird me out because I have not seen
And
them.
honestly, I wouldn't write them if I had I really want to get stacked blackboards so I can write taller, but I'm running out of room, so that's why I use them. And they're also used in a lot of mathematics courses. This symbol is really easy. This reads, C is a real number. That's all that that means. So technically it means is an element of the real numbers, but you can think of it the same way. So if I write a letter, epsilon symbol, a fancy looking R, that just means that that letter is representing some real number. That's all that it means.
Okay, thank you.
If I change it up maybe and say n epsilon fancy looking n, what does that mean? It just means that n is a natural number. The epsilon just means contained in the number system on the right-hand side.
Got it. Thanks.
Yeah, you have a question? Yes, other question.
Yes, so for the solution, you said you would want us to write it in an exam, correct? Would you want us to do the same process as you did, or can we just plug in 2 and then process it from there and just
get that theorem now and just plug in 2.
Okay, so we could
I'm not going to worry about it because, well, when I gave you the solution prior, we didn't know about that theorem. But now that I've given you that theorem, you can use it.
Okay, thank you.
Okay. But yeah, so now that we have that theorem, we might be able, as I was about to mention, that we can deduce something else. We can find a corollary or a true statement that follows directly from this theorem. That's what a corollary is. So recall that a rational function R of x, maybe, that's what I'll denote it by, is a ratio of polynomials. For example, R of x might equal some polynomial P of x over Q of x, for example, right? So That's the definition of a rational function. Now, we know that polynomials are easy to evaluate with limits now because of that theorem. We also know from this previous theorem that the limit of the ratio is equal to the ratio of the limits provided the denominator is non-zero. So this and that imply the following corollary to this theorem. So if r of x is equal to p of x divided by g of x, where r of x is a rational function, and the limit as x approaches c f of x, or I'll say p of x, sorry, equals L, and the limit as, actually, well, I'll just write it all out. The limit as x approaches c to g of x equals k, which is not zero, then the limit as x approaches c of r of x equals k over L. Okay, so that really is a consequence of this theorem and that theorem, because rational functions are ratios of polynomials. Actually, I wrote that wrong. So this limit is equal to p evaluated at c divided by g evaluated at c. So a rational function is a ratio of polynomials. Polynomials, you can just plug in the limiting value to get the limit. If the denominator limit is non-zero, then we can apply this guy right here. That's the result. So what you should take away from this is that smooth, continuous type of functions like polynomials are easy to evaluate limits at. You can just plug in the limiting value. If you have a rational function and the limiting value of the denominator is non-zero, super easy to calculate the limit. You just plug in the value c into the numerator and denominator polynomials, respectively. Super easy to do. So let's look at an example. Find the limit as x approaches 1 of the rational function x squared plus x plus 2 all over x plus 1. Okay. This is super easy to do. Rational function. I'll write out my solution and explain along the way. So this value here in the numerator, x squared plus x plus 2, it's a polynomial. We can just use that theorem right there, plug in 1 into it and see what it equals. And then also, the numerator is a polynomial that if we evaluate the limit by simply plugging in 1 into it, it's non-zero. We just take the ratio of those limits. So the solution is something like limit as x goes to 1 of x squared plus x plus 2. We just plug in 1 into that, so we get 1 squared plus 1, 2 plus 2, 4. So then we next evaluate the limit of the denominator. That's a polynomial. We can just plug in the limiting value, 2. So then by that theorem, the limit as x approaches 1 of the ratio is just the limit of the numerator divided by the limit of the denominator, 2. Done. Not so bad.
Professor, I had a question.
Yes.
For the solution, x squared x plus 2 over x plus 1, can we factor the numerator and then cancel the numerator with the denominator and plug it in with the
we will get there, actually. So these are what's called, if you remember from pre-calc, removable discontinuities. Now, I'm not sure that we can factor the numerator here. X squared plus x plus 2. If you were to try to factor this, you would think about what two numbers multiply to be 2 that add up to 1, which is the coefficient of x. I don't think we can factor that in that simple way.
Okay.
I think x plus 1 is a factor of that, right?
Yeah.
But we will maybe mention it now. Actually, we have a theorem to talk about first. Another theorem. Lots of theorems because we're learning how to calculate things, and mathematicians prove these theorems for, well, in some instances to be useful. I don't think that all theorems are useful, but at least in calculus. Why am I spelling things wrong? Okay, so next theorem. Okay, so let n be a natural number. There's that notation again. N is a natural number this time. So a counting number, 1, 2, 3, 4, so forth and so on. If n is odd, then the limit as x approaches c of the nth root of x is equal to the nth root of c for all c. And this holds for even n. So for n even, only when c is greater than or equal to 0. Okay. Now, why the weird wording of this theorem? Recall that if you're if you have like a radical with a odd power, right? That odd power is going to convert the inside, the argument of it. If it's negative, it will become positive, and you won't have a problem with like taking square roots of negative things. If it's even, however, you're going to return back and have an issue with that. Okay, so maybe I kind of worded that a little bit bad. I encourage you to, for example, if c is negative and n is 3, taking the cube root of a negative 3, what do you get? Versus if n is 2 and c is negative, you will get a problem. Let's put this the same. Here, being weary of the time right now. In fact, I think the rest of my lecture can wait till next time. So I'm going to go ahead and stop the recording here. However, I will post another recording following up this video on using these rules to solve various problems. But next time we're going to look at finishing out the section on evaluating limits.